Look at how to do some calculations of probabilities. So, we're going to first start off with suppose a die marked with the words amatic is rolled 10 times, and how often each side comes up is recorded, and that's where it's recorded here. So when you first look at this, you might wonder some things, you might notice some things and wonder some things. I do notice that one seemed to come up an awful lot, and none of the other sides came up as often. Makes me wonder about the die. Suppose a plain white die is rolled 10 times and how often each side comes up is recorded. So here, again, we've only rolled it 10 times, but it looks like what I noticed here is that some of the numbers seem really close to each other. Um, 6 seem to come up a few more times than not, but it still seemed to be about the same. So we want to find the probabilities, and that gets us into something called the experimental probabilities. The experimental probability of an event is how often the event happens over the number of times the event actually took place. So the probability of an event would be X, how many times it happened, over N, where X is the number of times it happened and N is the number of times the experiment was repeated. So find the experimental probabilities for each side of the die marked with the amatic and with the white dice. So let's first do the amatic one. So I noticed it went 10 times. There's 6 plus 3 is 9 plus 1 is 10. So 10 times it repeated. There were 6 here, so this is going to be 6 divided by 10. Then I noticed this one was 3. That'd be 3 divided by 10. I noticed the next one was 0. So 0 divided by 10. I believe the 4 was 1. Yep. 1 divided by 10. And then the other two were 0. By the way, I don't reduce these. I like to know how many I've done it. So it's more interesting in probability to leave it as an unreduced fraction. So you can see kind of how many it actually did. Now let's do the same thing with the other die. So the other die, it was 1 out of 10. Then the next one down, I believe, was 2 out of 10. The next one down was 1 out of 10. So 3 times, one time the number 3 came up. The number 4 came up 0 times. The number 5 came up 2 times. No, 4 times, I believe. Let's go look because I already forgot what it was. Yes, it was 2 times. And then the last one, I actually don't have to go back and look because I know it's 1 plus 2 is 3 plus 1 is 5 plus, wait, I messed something up. 1 plus 2 is 3 plus 1 is 4 plus 2. Oh, I just can't add. 1 plus 2 is 3 plus 1 is 4 plus 2 is 6. So there must be 4 left over. So there were 4 times for that. All right. So how could we make this more accurate? I want you to think about that for a moment. What do you think we can do to make this more accurate? And then I would say the way I would make this more accurate is to repeat more often. Once was not enough. 10 times was not enough. So I probably need to repeat more times. So I need to increase that sample size, that repeated times. Now, those are experimental probabilities because we actually did the experiment and then we calculated the probabilities from doing the experiment. There also are theoretical probabilities. The theoretical probability of an event is the number of ways the event can happen over the number of outcomes that make up the experiment, provided that the outcomes are in fact equally likely. And equally likely means that each outcome has the same chance of happening. So the probability of an event is the number of ways the event can happen over the number of outcomes in the sample space. The listing of all outcomes that are possible in an experiment is called the sample space, and the listing of other ways an event can happen is called the event space. So I'd like to find the theoretical probabilities for a fair dice. So first thing I'm going to do is list the sample space of throwing a fair dice. This doesn't mean to say 6. That's how many sides there are on a dice. It actually means to list the sides. List what you can actually get. So my sample space, and I'm going to use set notation. So it's a bracket, curly bracket. And I can get a 1, I can get a 2, I can get a 3, a 4, a 5, and a 6. So I'm actually listing what ways they can happen. Then I notice once I count 1, 2, 3, 4, 5, 6, there are 6 different outcomes in my sample space. Now I'd like to find the probability of getting a 1. This 1 is written as an event space, so there's one thing in there out of 6 things in the whole sample space. So 1 out of 6 is that probability. 2, I see I have one way to get a 2 in my sample space out of the 6 ways that are in my sample space. Same with the 3. There's one way to get a 3 in my sample space. So it's 1 out of 6. Same thing with the 4. There's one way to get a 4. There's one way to get a 5. And there's one way to get a 6. So there's my probabilities. This was written in the proper notation with the curly brackets. This means it's an event space. And so you want to kind of do that. And one of the things I noticed when I did my experimental probabilities is my amatic die was nowhere close to those numbers. Nowhere close at all. 6 out of 10 is certainly nowhere close to 1 out of 6. And 3 out of 10 is nowhere close to 1 out of 6. 1 out of 10 sort of is, but 0 out of 10 certainly isn't. So none of these numbers are close to what theoretically we should get. On the other die, they're still not close, but they're getting a little bit closer to them. There's a little bit more, and I bet if we increased our sample size, we'd see that even better. So this is known as the law of large numbers. The law of large numbers is as the number of times an experiment is conducted increases, the experimental probabilities approach those actual probabilities. Sometimes they're the theoretical, and sometimes they're not. So like with the amatic die, they were not the theoretical probabilities. They were they were calculated prior to doing they weren't done they weren't the actual value, which tells me that that die that amatic die has something wrong with it. The sides are not equally likely, which most likely means that the die is not is weighted die. The other one probably is closer to fair die. We don't know that for sure unless we completed the experiment a whole bunch of times, but most likely it's probably pretty close. But they both have actual probabilities out there. It's just that we don't know what those are unless we did the experiment a whole bunch more times. And even then, it would still be an approximation. But we get an idea of kind of what's happening with those. And so we can see the white die may be fair, and the amatic die certainly is not. All right, so now another example is according to the article, hip hop is turning on Donald Trump. Rappers love Trump's money, but now they hate his politics. Many hip hop songs mention candidates who ran for presidential elections in their hip hop songs in 2016. Some of the comments were positive and some were negative. The dataset is called hip hop. It's in what's called the 538 package. And this command will create. So I'm sorry, I don't know why I have that on there. We need to create a contingency table for that. So we're going to create a contingency table for this. So what I need to do is I need to go back to the top and run my setup package. And I'm going to actually clear out my one that was in there before. And then I'm going to run this one. Oh, I know why. I'm going to put in data 538. No, that's the package. So the data is the hip hop. There we go. So now my hip hop is in there. I can now see it's there, and I can come back to my probability. All right. So now we're going to create a contingency table. I'm going to look to see what my variables are. I would like to look at a contingency table of the candidates and whether or not the comments were positive or negative. That's known as the sentiment. So I'm going to create a table. We are going to use the tally command. And the tally command is going to use the variable candidate. And with it, I'm going to do the sentiment. And then I'm going to use my data is equal to my hip hop. And I'm going to do something called margin equals true. And what that will do is that will just show me what the totals are. So here I get this. Now this was 2016, so these are not people that ran recently. These are people that ran some time ago. And we can kind of see what's going on. And here's our values. It didn't, oh yes. So here's my, didn't give me my other totals. I think I know what it is. I want this to be a plus, and I want this to be tilde. There we go. So I want the tilde there, and I want to add them together. Now I've got my totals. Okay, perfect. So we're going to assume that this represents the entire population of all songs that are out there. We don't know for sure, but we think it is pretty done. So we're going to select a song at just random. And we want to compute some probabilities of that song. So we want to find the probability that the song is about Donald Trump. So that would be Donald Trump is here, and there were 268 songs about Donald Trump out of the 378 songs. So 77 songs. So we happen to have 268 divided by 377. And there's my probability. Again, I don't make this into a decimal. You can if you want to. You can make it into a percent. I don't reduce them. All right, so now let's find the probability the song has a negative sentiment. So a negative sentiment is right here. There were 71 songs that were negative out of the 377. So that's the probability of negative, and that's 71 out of 377. So even though I haven't calculated these as decimals, I can tell that this number is much smaller than this one. What's the probability the song is about Hillary Clinton? So that would be 92 songs were about Hillary Clinton out of 377. So 92 out of 377. And again, I haven't calculated them, but I can see that this is much smaller than the songs about Donald Trump. Probably the song is about Ted Cruz. So coming up here to Cruz, there was one song about Ted Cruz. So that'd be 1 out of 377. Now I'd like to look at the probability the song has a positive sentiment. So if I come up here, positive, there were 178 out of the 377. There are more positive songs than there are negative songs. So now what's the probability the song is about Donald Trump and has a negative sentiment? So one thing to notice is that something is an and, it means both things have to happen. So it has to be about Trump and negative. Both things have to be true. It can't just be one or the other. So we're going to come down to here with and means both things. So here's Donald Trump and here's negative, and they overlap right here at that 34. So this 34 out of 377. The probability that the song is about Hillary Clinton has a negative sentiment. Again, the and means both. So Clinton and negative. So again, I come over here to Hillary Clinton, negative. There were 16, I'm sorry, there were 29 out of the 377. So it does seem that there are more songs that were negative about Donald, the probability was higher that it was about negative and Donald Trump than it was about Hillary Clinton and negative. Now let's find the probability the song is about Ted Cruz and has a positive sentiment. So Ted Cruz and positive, well, there were none. So this is going to be 0 out of 377. And I usually do write that one as just 0. But it's kind of nice to know that's out of 377. So now what I like to do is I like to find the probability the song is about Ted Cruz or has a positive sentiment. So now let's think about what or means. Or means one or the other or both could happen. So it could be about Ted Cruz. So there was one song that was about Ted Cruz. It could be positive. And so there were 178 that were positive. So we add up the 1 and all of these, we get the 178 plus 1, which is 179 out of 377. So that's the or means we're going to add them kind of all together. So now we want to find the probability about Donald Trump or a negative sentiment. So that means, again, one or the other or both. So coming back up to my contingency table, it's about Donald Trump. There were 268. It's negative. There were 71. But what just happened is I just counted this one twice. So if you think about it, you can add all of these up and then add up these two left. So it's going to be the 268 plus the 1, the 29, the 5, the 1, and the 1, and the 2 zeros, but those don't matter. So we actually can see that it's going to be 268 plus 269, 270, 271, 276 plus 29, 276 plus 29. And just because I can't remember numbers as well as I'd like to, I'm going to write it this way, and then I can add them up. So 6 and 9 is 15. 2 and 7 is 14, and 2 and 7 is 9, and 1 is 10. And 2 plus 1 is 3. So it's 305 out of 377. All right, so now let's find the probability the song is positive, negative, or neutral. So it could be positive. There's 178 songs that were positive. It could be neutral. There were 128 songs that were neutral. It could be negative. There were 71 songs that were negative. We could add those all up, and we're going to get 377. So that would be 377 divided by 377, which you can, if you want to, reduce that to 1. Okay. Let's look at the probability that the song is about a Republican. So that means we need to know who the Republicans are. So Ben Carson was a Republican. Chris Christie was a Republican, so that's 3. Donald Trump was a Republican, so that's 268. Jeb Bush was a Republican, so that's 9. Mike Huckabee was a Republican, so that's another 2. And Ted Cruz is a Republican, so that's 1. So we're going to add 1 plus 2 is 3, plus 9 is 12, plus 92 is 104. I'm sorry, not 92. 1 plus 9 is 10, plus 2 is 12, plus 268, 8 and 12. 268 plus 12 is 290 plus 2 is 292, 294, 295. So we get 295 out of the 377. Now let's find that probably the song is not about a Republican. So going back up to my chart. Hillary Clinton is not a Republican. That was 92. And Bernie Sanders was not a Republican. That's 2. So 94 would be that number. Okay. All right. So if you were to find the problem of a person making a free throw, what information would you need? So this is just a totally different question. And I believe the information you kind of need is you need to know how many attempts and how many were made. So that's what you want to look at, is how many times did they try and how many did they actually make. All right, so let's get some probability rules. A probability is always a value between what two numbers? So if I go up here and look at this, I notice the smallest number I got was 0, and the biggest number I got was 1. So it's always between 0 and 1. And then the next question is the probability of all the outcomes in a sample space must add up to what number? Well, looking at this, I noticed that when I had all of the different things, I had positive, negative, and neutral together, those three together, I got 1. So it always has to add up to 1. All right. I'm going to talk about a couple rules here. So we're just going to do some ideas here. Complement rule. The definition of a complement is that the complement contains everything that is in the sample space that is not in the event A. The symbol for the complement of an event A is either not A or A with a little C in it. There's other ones too, but these are the more common ones that we see. I want you to argue that the song is about a Republican and the song is not about a Republican are complements to each other. Well, either the person's a Republican or they are not. That doesn't mean they're Democrats. It just means they're not a Republican. And in fact, Bernie Sanders is an independent, so he's not a Democrat. So we're not looking at being Republican or Democrat. We're just looking at being a Republican or there's something else. So that would make that they are in fact complements. What does the probability of a song that is about a Republican and the probability the song is not about a Republican add up to? So I want to remind you that we did this. We found the probability of Republican, and I want you to add that to the probability of not a Republican. And so we had 295 out of 377. And we're gonna add that to not a Republican was 94 out of 377. I must have added something wrong because that's not going to add up right. So I must have added something wrong. I hate when I do that. So 1. So Hillary Clinton was 92 and Bernie Sanders is 2. So that's definitely 94. So I think I added the other one wrong slightly. This must be 96. So 296. And when I add those two together, 4 plus 6 is 10. 9 plus 9 is, so it must be So let me go add these because I'm obviously not adding correctly. So let me add them correctly to get the right number there. So I'm going to add in R chunk and let R add it for me. So I'm adding 1 to 2 to 268 to 9 to 2 and a 1. So 280. 1 plus 2 plus 268 plus 9 plus 2. Oh yeah, 283. Okay. So that's what that adds up to. So that's that probability. I apologize for being wrong. It's always fun to be wrong. And so that was 283. All right. All right, so 3 plus 4 is 7. That's much better. And 9 plus 8 is 17 and 17. And 2 plus 1 is 3. So we get 377 over 377, which is the number 1. So it looks like it adds up. So it looks like a general rule would be the probability of an event plus the probability of not the event is always going to give you 1. Which means if you want to find the probability of one of them and you know the other one, all you have to do is subtract from 1. The last concept I want to talk about is mutually exclusive. What do the probability of a song is about Ted Cruz and the probability of the song has a negative sentiment add up to? So what I want to look at is just look at those two probabilities. So we have probability the song is about Cruz, and I want to know what that adds up to with the probability of positive. So we did those calculations up here. So we'll go back up to our calculations. So we have positive is 278 out of 377. Ted Cruz is 1 out of 377. So we have 1 out of 377 plus, and I've already forgotten my number. I should have copied it. Positive was 178 out of 377. So adding those two numbers together, I get 179 out of 377. What do the probability of a song is about Donald Trump and the probability of a negative add up to? So again, we'll go back up to the top, get these probabilities because I don't remember what they are. We did calculate these already. So Donald Trump was 268 out of 377. And the other one was negative 71 out of 377. And those add up to 7 and 1. 8 and 1 is 9. 7 and 6 is 13. 3 and 2 is 5 and 1 is 6. Well, there seems to be a serious problem because I can't get a number bigger than 1 because I just said I can't get a number bigger than 1. So I'm wondering what's happening with this that I can't get these answers. So notice that the probability the song is about Donald Trump plus the probability the song is negative does not equal the probability the song is about Donald Trump. Or has a negative sentiment. So those don't seem to add up. So this is what we came up with. But when we did the probability, I'm going to copy this and put it down here. This or statement they don't add up to the same. So noticing that they don't seem to add up to the same number, they don't seem to happen. But when I look at the probability of a song is about Ted Cruz and positive, sorry. I'm going to bring that down here so we can look at both of them. That does add up to what we got when we added those two together. So sometimes I can add those two individual probabilities together and get the right answer, and sometimes I cannot. And the question is why? Why does it happen in the first and not in the second? And if I go back to my contingency table, what I noticed in this contingency table is that there was no overlap with Ted Cruz and positive. There was 0 people here. Nobody was both. But with Donald Trump and negative, there was overlap. So what we did is when we added these two numbers together, we added this 35 twice. And so that's where our problem came in to be. And what this means is we get a new concept called mutually exclusive. Two events are said to be mutually exclusive, or another name is disjoint, if they have no common outcomes. Another way to think of this is that they cannot happen at the same time. So in the hip hop situation, there were certain songs that couldn't happen at the same time, or certain things that couldn't happen at the same time. I cannot get a song that's about us two candidates at the same time. But I also can't get a song about Ben Carson and be neutral at the same time. I can't even get a song about Ben Carson and be negative at the same time. Bernie Sanders, I can't get a neutral song about him. Chris Christie, I can't get a positive song or a negative song about him. Jeb Bush, I can't get a positive song. Mike Huckabee, I can't get a negative song. Ted Cruz, I can't get a neutral or a positive song. Sorry. Mike Huckabee was negative. I'm positive. So those are all mutually exclusive events. So I could list them all here, but that's basically what you're going to look at. Is you're going to look at all of those things, any of the ones where they have zeros. So Ben Carson and positive, any events where the intersection is 0. So now we're going to come up with some general rules for mutually exclusive events and events that are not mutually exclusive. So if the two events are mutually exclusive, what's the probability of A and B? In other words, what's the probability that both will happen at the same time if they can't happen at the same time? That would be 0 because they cannot happen at the same time. What's the probability of A or B? Well, that's the probability of A or B. We saw that when they were mutually exclusive, when we looked at Ted Cruz and positive, they were mutually exclusive. So it'd be probability of A plus the probability of B. There's no overlap to do anything with. If they're not mutually exclusive, then the probability of A or B, I can't just add them together. If I just add them together, I've just counted things twice. So I need to subtract off that overlap. And that overlap is the probability of A and B. And there's your formulas.